put all this together. We have a 10 kilogram traffic light suspended from a beam as shown. Find the tension in each of the three cables, T1, T2, and T3, supporting the traffic light. Well, what we'll do is let's start off by looking at what we have here, and I'm going to analyze our object as this one right here. So we have on that little ring, we've got T3 up is one force, tension from the rope, and we have mg down. And the net force in the y direction then, let's call up the positive y, is going to be, well, now all I do is add up all my forces in the y. I've got T3 positive minus mg, and because it's just sitting there, it's at equilibrium, no acceleration, the net force is going to be equal to 0. There's no net force. Therefore, I could state that T3 equals mg, or T3 is going to be equal to m, 10 kilograms, times g. We'll round that off to 10 meters per second squared, or 100 newtons. Okay, well, let's take a look at the ring itself then, now that since we've already done the light. If we look at the ring itself, we'll draw a free body diagram for it, and I'm going to draw my axes here first. X. Make these pretty small because we have a little bit of math to do here. Perhaps extend that a touch. All right. So looking here, there's our object. We have, pulling on it, T3 down. We have T2 to the right, which is going to have an angle of 30 degrees. There's T2. And we have T1 up and to the left, an angle of 60 degrees. So, if we wanted to break that up for a pseudo free body diagram, I'm just going to redraw that over here a little bit further on the left. Well, we don't even have to do that. Let's just keep going with our components and get through this. The net force in the x direction, if we look at this, we're going to have T2's x component, which would be T2 cos 30 degrees. I think you can see that right from the diagram. Going to the left, we have the x component of T1, which will be minus T1 cos 60 degrees. And all of that has to equal 0. And we could try the same thing for the y direction. The net force in the y, which just means add up all the forces in the y direction. We're going to have T1 sine 60 degrees plus T2 sine 30 degrees minus T3, which is 100 newtons, so minus 100 newtons, all has to equal 0. So those are the equations I have to solve in order to find my tensions. So let's take a look here. I'm going to go back to my green one, my net force in the x direction, because it looks like with just a little bit of math, I can find T1 in terms of T2. So if T2 cos 30 minus T1 cos 60 equals 0, I could write that T2 cos 30 degrees equals T1 cos 60 degrees, or T1 is going to be equal to T2 cos 30 degrees over cos 60 degrees, which is about 1.732 T2. So T1 is that factor times T2. We can take that and plug that into our red equation, the net force for the y direction, by writing that T1 sine 60 degrees plus T2 sine 30 degrees equals 100 newtons. Which implies then, since we know that T1 equals 1.732 T2, we can replace T1 with that. So we have 1.732 T2 sine 60 degrees plus T2 sine 30 degrees is going to be equal to our 100 newtons, which implies then that, well, we do all that together, I get 1.5 T2 plus 0.5 T2 equals 100 newtons. Therefore, T2 must be equal to 50 newtons. And once I've done that, if I know T2 is 50 newtons, I can plug that back into here for T2 to find that T1 is 1.732 T2, which was 50 newtons, or 86.6 newtons. So we found the tensions T1, T2, and T3 in our suspended traffic light. All right, hopefully that gets you a good start with Newton's first law free body diagrams, and we're going to continue to work on these and evolve them as we go through the course. Thank you so much for your time, everyone, and make it a great day.